So let's get started. So we learn. Is it okay? No. So this is better. Okay. So we learned that so the Jones polynomial is a quantum invariance coming from Wilson loop, and it's a Laurent polynomial, not K. Okay. And so today I'm only talk about the color is the representation, which is often called color, is the fundamental representation. Okay. And the gauge group. So this is Jones polynomial. So Jones polynomial is SU2, G is equal to SU2 case. In general, also in this talk, I just talk about SUN, SU2 to SUN. So in general, one can talk about the SUN case. So today's focus is this one. And for instance, so this is actually Laurent polynomial. With respect to variable q. Okay. So sorry, I should mention this is the same as GR, not so the Wilson loop exponential value when G is equal to gauge SUN. Okay. And R is in this case fundamental representation. And what Komarov did is as follows. So you associate. So this is the equal. Instead of considering the quantum invariance, you just given a knot, you assign a vector space. So vector space. Okay. And I and J are the grading. So doubly graded. Okay. And whose dimension? So you and no. So this is the vector space. So the bi-graded, that's bi-graded vector space. And he constructed in such a way that the dimension of the Hij k, okay, Hij, and take the Q-graded Euler characteristic, Qi, but take -1 to the j, and sum over I and j. So this is equal to the quantum invariance. I would say quantum invariance of the R equal to K and Q. So given the knot K, so you can construct, given the knot K, so you can construct the bi-graded vector space, which is called common homology, common Horosansky homology, and whose Q-graded Euler characteristic. So if it is the single graded, it's just Euler characteristic. But here you have a weight by Q degree. Okay. It's the quantum invariance of the knot. Okay. So that's what. So this procedure is often called categorification. Okay. And it.
So this explains why the coefficients of the Laurent polynomial are integrated.
Yes. So with integer coefficient. So the Laurent polynomial with integer coefficient, and from this construction, it's very natural because it's just dimension. Okay, so from vector space to the integer taking dimension, this procedure is often called, just taking dimension, or sometimes called decategorification. And what's nice about it, it has more information, okay, than the quantum invariants are not. Okay. And moreover, so there's a mathematician here. So it is endowed with a rich, like a differential structure and so on. And so the Komarov, so this is work by Komarov in 2000, around 2000. And he works on the SU2 case. G is equal to SU2 case first. SU2 case. And later, so in 04, Komarov and Rozansky define G is equal to SUN. Okay? SUN 04 by using so-called metric factorization. So which I'm going to explain this in these lectures. Okay.
So you have some, you're saying you have some homology factor assigned to some category, but will you describe those categories?
This is 2 categories and so on. No, I'm not gonna describe. I can explain to you impersonally, but yeah. Okay. And furthermore, so we learned that so when you take large n limit, one can associate the two. Let's see. I will use P actually instead of J. Where when you take A is equal to Q limit, so when you take A is equal to Q limit, A is equal to Q to the n. Okay. It reduces to the SUN invariance. This is called Humphrey polynomial. Humphrey PT polynomial. And I also only focus on representation as fundamental representation. Okay. And the Komarov-Rozansky, and there is a 2 paper by the Komarov-Rozansky in 04, at least on the archive, not published year. Again, Komarov-Rozansky actually categorified this Humphrey polynomial, and they constructed triple graded vector space, okay, in such a way that the dimension of this I, J, K, not K, and just summation A, I, Q, J, and minus 1 to the K. And the sum over I, J, K is equal to this Humphrey polynomial. Okay. So this is triple graded homology. So triply graded homology. Triple graded homology. Yes. You don't need you don't need the information about the quantum invariance. Just given a knot, there is a procedure to construct this triple graded or bigraded homology. So that's what I'm going to explain. So using metric factorization. So this is triple graded one. Okay. And there is a procedure to go from here to here. So at the quantum level, so you just substitute A is equal to Q to the N. Okay. But from triple graded to doubly graded, you take the so-called differential, so-called dn differential. Yeah, it's a dn differential. So that the given that triple graded homology, the differential acts on, and take the homology with respect to dn differential, and what you get is this doubly graded homology. So this differential is constructed. First, first predict by the Google Rasmussen downfield, Gukov downfield, Gukov Rasmussen, and this is conjecture, and the sum. So and the rigorous construction given by Rasmussen. Yes, and the physicists predict, as I mentioned to you, the physicists predict this Hij and this bigraded vector space and the triple graded vector space is essentially the H naught. The basic idea of the physicists have is H naught. This homology, not homology, is the space of BPS states. So this is a basic idea physicists have. And in particular, so it has the A grading. So therefore, the triple graded homology associated to BPS states in resolved conic foci, whereas the bigraded homology is associated to the BPS states in deformed conic foci. Okay, there's no A grading in deformed conic foci, if you remember. Okay. So that's the difference. So this is deformed conic foci, and this is resolved conic foci. So as you, if you remember, so deformed conic foci T star, Calabi-Yau is T star S3, deformed conic foci. And by geometric transition, if you take large N limit, large N limit, so the T star of X is so transformed into the resolved conical. And yesterday I mentioned that the A parameter is associated e to the minus volume of CP1. Okay. So therefore, the A grading only appears in this side. So therefore, BPS states on the resolved conical side is associated to the triple graded one, whereas the bigraded homology is associated to deformed conical. So that's the main idea of physics. That's it. But today I'm just talk about the construction in the Kolmogorov-Rosansky in the bigraded and triple graded one by the metric factorization. Okay. So this vector space itself. So I'm going to explain the construction I'm going to explain is itself is not invariant. This vector space is invariant under Riemann the 2 and Riemann 3. So therefore, one can consider instead of taking the Q-graded Euler characteristic, you can consider the Poincare polynomial. So therefore, so from I, J, so one can construct a sum of Tj, Qi, dimension of H, I, J, K. Associated. So this is called Poincare polynomial. I will use the Cayley P of the K, Q, T. And when you take t is equal to -1 limit, it reduces to just quantum invariance. Okay. Similarly, so if you have a triple graded homology, you can assign the K, AI, QJ dimension H, I, J, K. Like this way. And it's this polynomial called, people sometimes call this one is super polynomial. I think this name was introduced by these guys, Dunfield, Google, Rasmussen. Anyway, so it's just Poincare polynomial of the triple graded homology. And when you take t equal to -1 limit, it's the t equal to -1, you get the quantum invariance. So SUN version of the Jones polynomial, and this is a Hong-Hou polynomial. When you take t equal to -1. Okay. So therefore, t equal to -1 is the categorification. Sometimes the grading of t grading is called homological grading. Okay. So the construction is given by so-called metric factorization. So the matrix factorization, can be explained without physics, but most of the people are physicists. So this is actually introduced by Eisenberg in long time ago, but it appears in physics as the boundary condition. B type means the supercharge is preserved at the boundary is like a B twist, B type boundary condition of the 2D Landau Ginzburg model. In particular, I'm going to consider the following case. So the matrix factorization given by follows. You have a Z2 graded vector space, in this case ring, and you assign a so-called the map in between. So the R0 and R1 is given by the polynomial with respect to x and y. Okay. Then the d plus, if you compose this differential, it's not, a standard differential. This map is given by W1, W of x, and x minus W of y. And this W is a function of the function. So sometimes it's called Landau-Ginzburg potential. Just superpotential. This is superpotential. It's often called superpotential. So in schematically, people has in physicists always write down picture. You have some boundary condition whose the potential is given by Wx and Wy. So this is a boundary condition, and the region is called X and Y. Yeah. 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 And also, so this is two-dimensional. So I just try to draw the two-dimensional picture. So this is two-dimension. It's just plane, and you can just it's a Lagrange model is a topological tree. So therefore, you can do the folding. You can just take the folding trick. It's called folding trick. And this is a boundary condition here, given by here. And the superpotential described by W of X and the minus W of Y. Okay? Minus W of Y. So you can just fold this one into here. And then you get the standard boundary condition, whose potential given by W of X minus W of Y. Okay? But as a mathematician, you just given this rule. Okay. So sorry, and X and Y can be considered. So X and Y can be considered as the. I think I should use the position. X and Y can be considered the chiral field, chiral superfield of the Lagrange model. I mean, as a mathematician, it's just formal variable. X and Y can, for physicists, X and Y can be considered as the chiral superfield. Okay. Then, so if you have a two type of boundary condition, let's see. Yeah, I mean, more generally, one can have the different potential W1 and W2 in more generally. W1 and W2. W1 and W2. The function can be different. Okay. Therefore, you just assign so W1 of X, W2 of Y, W3 of Y, Z. And it's topological, so you can move the defects. You can freely move. It's topological. So therefore, you can take a fuse. Actually, you can take a fuse them together. Okay. And W1 of X, W2 of Z, W3 of Z. Okay. You can fuse. So I would say, so this boundary condition is, I call D, which stands for defect, D1 and D2, and D1 cross D2. So if you fuse them together, so you get some tensor product or metric factorization. So this is a new type of defect. So therefore, you can assign the following. Sorry, instead of one, let me use tilde. Sorry, tilde. Okay. So this is a new vector space, and there is a differential d0 r1 cross r0 tilde plus r0 cross r1 tilde. Okay. And a d1 r0 plus r0 tilde and a plus r1 cross r1 tilde. Okay. So this is tensor product of two metric factorization, and I assign d0 as the d plus cross identity identity cross d plus, okay, tilde, and minus identity cross d minus tilde, and d minus cross identity. So this is the map d0, and d1 is similarly one can construct identity minus identity cross d plus tilde, and the identity cross d minus tilde, and the d plus cross identity. Okay. If you define map like this way, then d plus d0 composed with d1 is equal to d1 composed d0, which is given by w1c minus w1 of x minus w3 of t. Okay. So if you take the tensor product, even if you take the tensor product, it's a fusion of defect, you get another new metric factorization which describes the new defect. Okay. And in particular, how is it related to the knot, actually? The question is. So Komarov and Rosansky construct the following metric factorization. So they're given a knot. So the, for example, okay, in a truffle. So at each crossing, you have a two new scaling relation. So so each crossing you assign. Okay, you assign the two metric factorization x2 so at each crossing you assign a two resolution. So this is called Moy graph, actually. Two metric factorization. At each crossing you assign two resolution. You assign a two resolution. Okay. So two types of resolution. This is introduced by Murakami, Otsuki, and Yamada. Okay. So the metric factorization, you just given a two by Z2 graded vector space, and in this case, so it's a polynomial ring, okay, polynomial ring. And you just assign a map in between d plus and d minus, which satisfy this condition, That's called metric factorization. And in each crossing, so you assign a metric factorization, R0, R1, R0, okay? And each resolution you assign the metric factorization, giving as follows: d plus, d minus, d plus, d minus. Such a way that the all R is given by C, x1, x2, x3, and x4. Okay. Divided by ring is given by x3 plus x4 minus x1 minus x2. Okay. Ring is given by all the ring is this one. Okay. Yeah. So W is given by W of x is given by x to the n for G when G equal to SUN. Okay. So this is superpotential. This is your superpotential. Superpotential. So I already started explaining Coburn-Hrozansky construction. Okay. Start explaining. So each map is given by here. D plus is given by x3 minus x1, x2 minus x3. Okay. Am I correct? Yeah. So D plus tilde is this one. So here, so you just assign the chiral superfield or just variable as a mathematician, like this way. And the D minus tilde is this one. Is given by W x3 plus W x4 minus W x1 minus W x2. Okay. Divided by x3 minus x1 and x2 minus x3. So therefore, as you can easily see, D plus tilde compose D minus tilde is D minus tilde compose D plus tilde is given by W x3 plus W x4 minus W x1 minus W x2. Okay. Now furthermore, so as you can easily see, so that you just assign x1 and x3 and x2, x4. So therefore, this resolution can be just put the D plus x3 minus x1. So therefore, so you just assign the x1 is the same as x3. So this means the x1 is equal to the same as x3. And if you use this relation, this ring, so this is the ideal generated by this relation. Once you impose the x1 is equal to x3, x2 automatically is equal to x4. Okay? So therefore, and d minus is given by the same thing. So the numerator is the same. Okay, divided by just this one, x3 minus x1. Okay. Therefore, so this is equal to d plus dot d minus is equal to d minus dot d plus is equal to this. So which one?
It's not obvious that the d minus is such a
Polynomial. Instead of rational function, you mean? This one is rational function. Once you plug in this one, yeah, sorry, they just polynomial, and this one, I think. Okay, but if you plug in this one into here, it's polynomial, right? But how about this one? To be honest, I don't know. But I just only know that the composition of two maps should give you this one. Yeah. Okay. Yeah, correspondingly, yes. Yeah, I think so. Yeah. Okay. So given the two metric factorization, so this is two type of defect, and it's called in mathematics it's called cone construction. So this is, I would say, so this, let's call this metric factorization is D. D, this one, D. This is called cone construction. Cone construction of D, this resolution to D. This in such a way that the D, they commute. So therefore, one can define dB as the x2 minus x3, and so dB0 and dB1 and dB0. B means vertical. Okay, vertical is equal to 1. And you assign at each crossing you assign this cone, the metric factorization. Okay, so physicists often said this cone construction will give you the bound states of two defects. So you just take without dV, there are two different metric factorization, but by using cone construction, one can consider the two balanced state of two defect. Okay. So therefore, so you assign, so this D crossing, okay, the defect is the cone construction of the dV, this resolution to this resolution. Okay. Such that the R1 often write R0 tilde. I mean, this is another way to write. Yeah, I would say R0 plus R1 tilde and R1 plus R0 tilde. And let's go C1 and C0. C1 is given by, so D minus D plus tilde 0 and dV, okay? And C2, sorry, C0 is given by D plus and D minus tilde dV, okay? Essentially, this differential is actually the supercharge in physics language. Supercharge is present at the boundary. Therefore, without dV, I mean, without dV, when dV is equal to 0, you have a just direct sum of two different defects. But once you turn on dV, you can consider bound states, okay, of the defect. So essentially Q boundary supercharges boundary. Supercharges without dV is something like a D minus plus, D plus minus, I think D plus minus tilde 0, 0. But you just deform the supercharge in such a way that the Q boundary plus delta Q boundary is given by D minus plus 0 dV and D minus tilde. Okay. I think I have to be careful about dB0 or dB1. I think dB0, dB, something like this. I may be wrong. Okay. So this is deformation of supercharges. So deformation of supercharges, boundary supercharges, leads to the bound state of the two defects. That's how physicists describe this cone construction. Okay. Okay, then, so what's going to happen as follows. So here, let's write the trefoil like this way. I think it's a. I think trefoil is given by like this way. I think. I hope I'm right. No. Sorry. I mean. Yeah. Am I correct? I just got confused. Is this? Anyway, so given a knot like this way, okay. So you just assign. So given a knot like this way, so at each crossing you assign this metric factorization. So you just assign. So there is some cylinder going on upstairs. At each crossing you assign the metric factorization. At each crossing you assign a metric factorization. Okay. And each crossing you assign a metric factorization. So you assign a defect. So at each crossing. And each segment you have a so you assign each chiral field x1, x2, x3, and here x4. I mean, whatever. x3 is the same. I mean, but at each crossing you assign something like x4, x5. I mean, and x5, and here the same rule appears. The x5 stays the same, but here you assign another variable, x6 and x7 and so on. Okay, at each segment, there are different chiral field, and they're identified to the right hand side. So you just assign x1 is here, and x2 is here, and x3. Okay, you can assign like this way. Then you assign the metric factorization at each crossing, like this metric factorization, and just take a tensor product. Okay, as I mentioned, you just fuse them together, the defect. And then at the end of the day, what you get is follows. So you just get the following bigrade homology. Let's see, C, J, I, D plus, and D minus, C, J, I plus 1, D plus, and D minus, C, J, I plus 2, and so on. Sorry, bigrade complex, actually, once you take the tensor product. And Cj plus 1, and I, Cj plus 1, I plus 1, Cj plus 1, and I plus 2, and so on. Okay. 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 So once you go around, okay, CJI is the CJI is essentially the essential this one. Oh, okay. So if you, okay, so you have the potential W1 and W2 and W3, and coming back to W0, right? So therefore, so at each metric factorization, you get the W1 minus W2 differential is W minus 1 W2, and W2 minus W3, and W3 minus W1. Okay, once you take the two differential. And if you fuse them together, what you end up is the W1 minus W1. Okay, 0, right? So that's essentially differential. D plus dot D minus becomes 0. Okay. So therefore, so this construction, once you fuse them together, you get just the bigrade complex. So where the upgrading is the grading by this dV. So the J grading is given by the grading in vertical direction, and the I grading is given by 0 and 1. I grading, so D plus and D minus. D minus. D plus and D minus. So the second gradient is Z2 graded, Z2. 0, 1, 0, 1, and so on. Yes, so J runs for the number of crossing. Yeah, that's true. J. At each crossing you have a step by one, and by one, and if you take a tensor product, you have a. I mean, you can take a J step by. R is the so this R is the horizontal direction, so it's just Z2 graded. But that's true. So this column can be identified this column in that case. Do you understand? Oh, okay. So I will explain to you. So this one is graded by Z cross Z2. Okay, I will explain to you. So it depends on the C depends on the variable x1 dot 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 many my Carl field, and this so I will say Q and QT. So this grading comes from the grading by x. So Q over x, the Carl field has depends on notation. I would say 2. I would say 2. And this is J grading. So J and this is I. So what I mean is follows. So let's see. CJI is some ring C x1 dot 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 xn, some variable. Okay. Divided by some relation. Relation. Divided, and it is actually the often finite dimensional actually. Am I correct? No, sorry, it's not correct. But each generator Q grading of x1 is given by. Okay, I will explain it in the example. I think it's better to explain the example. So in the case of trefoil, so example. So once you take the homology with respect to D plus and D minus, what you get is as follows. So this is the C of x divided by x. So trefoil and n is equal to 2. Sorry. So this dv and dv C of x square C of x square and dv. Okay, and you just get the 0. Okay. So in the trefoil case, once you take the differential with respect to d plus and d minus, so what's left is this vertical line. Okay. And this CGI is given by, so it's already collapsed to the only one column. So therefore, only j gradient are left. Okay. And it has a generator 1 and x. Okay. It has a generator 1 and x. 1 and x. Okay. Sorry, I told you wrong. This is x plus 1. Sorry, x plus 1. Yeah. Okay. X to the n plus 1. Yeah. Okay. And this dB is actually multiplication. Multiplication by x. Just multiplication by x. So therefore, this generator is mapped to this one. Okay. So dB is the multiplication. Once you compute the tedious homology, bigrade complex, one can show that dB is just multiplication by x, and in this ring, so the same ring, so generated just 1 x. Okay. 0. So once you take the homology with respect to d plus and d minus, the homology becomes the trivial, just 0. There is no generated homology. Whereas so this is j is equal to 0, j equal to 1, and j equal to 2, and j equal to 3. Okay. So dV is actually the multiplication by x. So what's left as a homology is these 4 elements. Okay. What's left in the homology? These are generated of homology, the common homology. And for x, you assign. So you assign the q grading. So from here you assign 1 plus q square. So x has a q grading square, but t grading is 0. Okay. T grading is 0. But here t grading is square, but you have only one generator. And after gradient shift, actually, let me just cheat here. And this Q6, so this has a generator Q3, Q38. Okay. This term, this generator X give you the Q gradient Q34, but T gradient is square. Okay, and 2, and T. Oh, sorry, 3. Sorry. T gradient is just J. And actually, so you have to shift by Q grading once you go upwards. And what's going to happen? This Poincare polynomial. So let's use the color P of K and QT. K is triple. 1 plus q square plus q to the 4t square plus q to the 8t cubed. Why is it j equal to 1? So once you compute the homology with respect to d plus and d minus, when j equal to 1 case, it becomes trivial. No, it's a hard computation. Yeah.
Because for x cube is only 1 between x and x squared.
Yes, yes. Uh,
But first of all, you have a single x because you have a single span. All the only a single component. That's why it's single x.
no, no. I mean, so the reason why I just take the differential with respect to d plus and d minus. That's why.
It's after fusion, right?
Yeah, after fusion. So
No, what is single? They're all the same.
yeah, but each crossing you assign it 4 variables.
If you want to identify
Yeah,
globally it's the same unit,
there's no link. But so I mean, the left side and right side they are the same, but in between you have to assign a different variables at each crossing, like this way. Even though they are but in the ring is you have to impose this condition, okay? And also d plus is given by this x1 minus x3. I think. And once you impose and take the fusion, what you end up with is the following complex.
Why is j equal to 1 special?
Why is j equal to 1 is special? Good question. It depends on not actually, because I mean it's just only 3 crossing. There is a 3 crossing. So therefore, vertical line can go only 3 steps. And so the Q gradient of x is given by 2, and up to appropriate gradient shift when you go to when you increase j, so you assign q to the 4th into here, and q to the 8 to this generator. And what you end up with this one, the Poincare polynomial. And what Kovalov-Rozansky showed that the homology of this bigraded complex. So this homology of what they claim is as follows. So H.
So, but with the default case, you are only finding one variable that is x, and you are assigning q to one gradient q.
Yeah.
But if you have a more complicated one,
Uh-huh.
so that even after fusion, you have maybe more than one variable, then why would it be a bigraded? With each variable, you will assign one different q. I mean, if you are saying j and after fusion x1 and x2,
Mm-hmm.
why not assign x1 and x2? Wouldn't you assign a z gradient to x1 and another z gradient to x2? That's not how it works.
So each gradient xi has a q gradient.
Yes.
Yeah.
So that so if you are so the number of variables will be left with more than one after fusion,
Yes.
then it will be not with the bigraded, because you already have a gradient j
Yes.
there.
Yes.
And
Yeah.
each xi you have another gradient you are assigning. So why would it only be a bigraded setup?
No, each variable assign this z gradient.
Same gradient.
The same gradient. Same gradient. R charge. Yeah. R charge. Yeah. 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 And this H star of the CJI, and first take d plus minus and take homology with respect to this difference of dv. Okay, so this is common homology. So this is the common homology. Komarov-Rosansky homology. No, Rosansky homology. Okay. So this is the bigrade one. How about triple graded one? Triple graded one is very easy. Triple graded one is you just put the potential is just zero. Zero. Okay. Put the zero. Then, so if you look it back, the definition of D minus becomes automatically zero. Okay. Okay. If you put the potential at zero, D minus is automatically zero, right? Then, so this D minus disappear. Then D2 grading becomes just D grading. Okay? And this is actually A grading. And that's how they construct a triple graded homology for Humphrey BD polynomial. Okay. And what they showed as follows. So they showed that this homology, triple graded homology, is invariant. Okay, maybe. So the paper is very wrong, but the construction itself is not that difficult. But the proof, so they proved this H is invariant under light dimension move 2 and 3.
So any understanding of why this
Good question. So, I mean, good question. The answer to your question, to be honest, I don't know. But they effectively, so so the once you recall the brain configuration out of 4 t to this S3 is a space-time, and the NM fibrans wrap from S1 cross R2 cross S3, and the MM5 prime brands wraps from S1 cross R2 cross Konoma bundle K. And so this cylinder part is actually, you consider S3. So this is cotangent, so the cotangent bundle of S3, and then you put the knot. So for instance, let's put the knot inside around the equator of the knot, the S3, like this way. Yeah, anyway. So equator of S. So this is inside, just thin tube. So the S1 cross, sorry, the S1 inside S3. So it's just equator in S3. And so what we speculate is this S. So the S1, this S1 times this S1, this S1. So the S1 sits in, is the intersection between S3 and K. Okay, so, which is not, but you just put the S1 inside the thin tube. You just squeeze into the not into a thin tube, and it becomes S1. So this product is essentially this cylinder. So this time direction is this S1, and this equator is given this thin tube, and the effect of this theory, which describes the physics on this plane, we speculate is the Lagrange model appears, but we don't have some like first principle explanation why the Lagrange model appears actually. Anyway, yeah. Fundamental, but one can, so this construction can be generalized to the R is, so representation, this representation so this representation R is equal to the, so this type of representation one can generalize. And to do that, one has, the superpotential is just, you have lots of variable instead. Let's go K. Where the K is number box. But for example, symmetric representation, one can apply this method. And recently, Sebastian Cotis has constructed the triple gradient knot homology colored by any representation constructed by using a different method. So this is the original Kolmogorov-Rosansky construction, but he used a different method to define a knot homology. So I think his method is cross-related to Affine-Grassmannian so on, I think. Affine-Grassmannian. So which is the infinite dimension analog of Grassmannian. Yeah. So that's the status of the knot homology. And nowadays, there's a lot of construction known, at least when the R is fundamental representation. There are many other constructions not rely on not without relying on this metric factorization. Yeah. BPS states is you just assign the supercharge which perturbed by this configuration, and is a state annotated by these supercharges is the BPS states. Oh, yeah, good question. So in the deformed corners of foci, you have a equivalent part of Q and T, right? So there's a two gradient coming from equivalent action. So there's a U1 Q and the U1 T, which acts on BPS states. Yes, yes, M2 brane. Yes, yes, yes. That will give you the BPS states. So the BPS state it arises from the M2 brane stretch M3 and MK.
Then this thing should be understood, right? You know roughly what the difference
Yeah,
atoms
yeah, yeah.
we want we should be using some introduction of
Yeah, I think so. Um, yeah, so there are lots of construction now, but the equivalence between these two different constructions are not proven yet. But everything reduces to the same answer. So the people believe all the constructions are the same, but the proof are not given yet. There are lots of people. Yeah, I mean, for example, there are lots of people working on this not homology. Webster, Williamson, and Cooper, Ben Cooper, and Kraskov. I mean, Stropel. I think Frankel, and I for somebody. And there are lots of people construct not homology in a different way. But the equivalence in between, and also, sorry, I should put Oblomkov and Lozansky. Yeah, and Kotis, Kamenitz. I mean, there are lots of people construct not homology in different ways after the common Lozansky. And the equivalence between them are not shown yet, but nowadays there are many constructions.